Good morning. Welcome to a new lecture in detection, and in today's lecture what we will do is first we will complete what we were discussing about waveform detection, and then we will start looking into performance of some signaling schemes. So, remember in the last lecture what we have said is that we have this random process which was infinite dimensional random process, and this infinite dimensional random process was projected on the signal space. Signal space is the space which is formed by these orthonormal functions, and when an infinite dimensional random process passes through this signal space, it becomes a finite dimensional random process, and by looking at this finite dimensional random process we can do detection optimally. That is, whatever we lost out because of this finite dimensional signal space was irrelevant for detection, right. So, hence when you go from waveforms to vectors, you lose out on something, and whatever you lost out is not important for your detection, it was really irrelevant for the detection. So, today what we will do firstly is we will form the optimum rules for waveform detection, and before doing that we have to revise some properties. Okay. So, that will help us in getting started. Alright. So, these properties we have looked in several times, and thus I will just state them, and if needed we will also look at their proof. So, if we have two signals AT and BT, and AKs and BKs are the coefficients of the signals along orthonormal functions, then if you want to take the inner product of these two signals, this inner product is same as the inner product of the coefficients. Okay. And these coefficients also are the elements of the vectors. So, if I want to think about the inner product of the signals, this is same thing as inner product of the coefficients, this is same thing as inner product of the two vectors A and B. Alright. So, that is the first thing. Second is, if you want to take the inner product of the signal with itself, this would be same as taking the inner product of coefficients with itself, and this thing is same as taking the inner product of vector with itself. And so, the energy of the signal is given by this. This is same as energy in the coefficients, and this is same as energy in the vector. Okay. So, all these things are equivalent, that is to say. Now, let us take the inner product of Vt with AJT. So, what is Vt? Vt is the infinite dimensional random process that was falling on the receiver. AJT is one of the signal from the signal set. So, we know that this Vt can be decomposed into two parts, one is V1t and V2t. In the last lecture we established that this is really irrelevant for detection, and this is only important for detection. Alright. So, you can take the inner product of this with V1t and inner product of this with V2t, and this is really 0, right. This we have seen in the last lecture, and thus thinking about inner product of Vt with AJT is same as taking the inner product of V1 with AJ or V1t with AJT, it is one and the same thing. Okay. So, these are the waveforms and these are the vectors corresponding to these waveforms, and we have already seen whether you take the inner product of the waveforms or the waveform vectors corresponding to these waveforms, it is one and the same thing. Alright. So, let us look at some optimum decision rule in discrete time additive wide Gaussian noise channel. So, this we have seen before. So, for discrete time was covered, I am just restating them, so that you can see that the rules for continuous time AWGN channel are same as the rules for discrete time AWGN channel. Okay. So, there we have seen that the receiver decides for the hypothesis J, and this hypothesis J is the one which maximizes this thing. Okay. This we have seen in the lecture. Now, what happens in continuous time case? Again is exactly same. So, I will just mention the changes. The changes are that in case of vectors we are thinking about the inner product of the vectors, but we have seen that this is same as taking the inner product of waveforms, right. We have derived that V 1 inner product with A j is same as V t's inner product with A j t. Okay. And we have seen that whether you want to think about the energy of a vector, this is same as thinking about the energy of the waveform. So, the rules for continuous time AWGN channel are exactly same as the rules for discrete time AWGN channel. So, in this case what we assumed is that these signals are complex signals, and when is the case? When we consider the signals to be complex baseband signals, right. So, we cannot transmit any signal which is complex. So, we can only consider complex signals in baseband domain, right. These signals are equivalent of the passband signals, this we have seen. So, whenever you are taking the real part of the signals and if the underlying signals are complex, it means that they are complex baseband signals. How can you think about passband signals? For passband signals exactly the same decision rule follows, but just simply instead of having real part, you do not have any real part because these signals are anyway real signals. So, what we can see is that these rules are exactly same. Let us look at something which is slightly different, mathematically slightly different. So, let us consider the case for ML detection. In ML detection, what happens is you do not have this term, because priors are equal. If the priors are equal, you really do not want to consider this term, right. So, in ML the rule is simply this: you want to choose j for which this quantity is maximum. In case for vectors, we said that this is same as minimizing the distance, maximizing this thing is same as minimizing the distance of V t from A j t, but you cannot state this in this case because this distance is infinity, right, because V t is actually infinite dimensional signal, all right. If you want to consider this distance would be infinity, and thus it is mathematically imprecise to find out the j for which this distance is minimum, because all these distances are actually infinity. So, you cannot state that ML in case of waveforms is really minimum distance decoder. However, if you want to think about minimizing the distance, then you have to think about minimizing the distance of V 1 t from A j t. Remember, V 1 t is the signal which is after the projection of V t on the signal space. So, that is really a small issue, mathematical intricacy, otherwise everything remains same. Okay, so, now let us look into this successive transmission. So, in case of successive transmission, now we have these symbols, and these symbols are riding on these orthonormal functions, and we also have orthonormal functions which are t spaced orthonormal functions in this signal expansion. So, what we are doing is we are having bunch of n orthonormal functions. So, let us assume that we have n orthonormal functions. So, we would be having the symbols which will be manipulating these orthonormal functions. For example, you may have a symbol u 0 which might ride on phi 0 t, and you might have u 1 which would ride on phi 1 t, and you might have u k minus 1 which is riding on phi k minus 1 t, okay, or rather phi n minus 1 t if you are having n orthonormal functions, right. So, in this case k might go from 0 to n minus 1. Okay. So, you have symbols riding on these orthonormal functions, and then you have next set of symbols which will be riding on the orthonormal functions which are derived by t spacing these orthonormal functions. So, in the next time slot you would again be having some other symbols which would be riding on the orthonormal functions which are t spaced orthonormal functions. Okay. So, this is in general the equation for successive transmission. We have seen such equation before, for example, in lecture 5 when we have done double sum expansion using Fourier series and DTFT, actually this is the basic equation that we had there. Okay. So, the equation is simple. You try to understand that you have bunch of orthonormal functions, these functions are orthonormal to each other, and when you T space these orthonormal functions, the new set of orthonormal functions that we derive are also orthonormal to these basic set of orthonormal functions. Okay. And this UKJ denotes that these are the choices that we make from this signal set. So, we have m signals and we make a choice, and accordingly we modulate these T spaced orthonormal functions. If number of orthonormal functions that we have is 1, then we are in the regime of pulse amplitude modulation. If number of orthonormal functions that we have is 2, if n is 2, we are in the regime of COM. If n is larger than 2, then we are talking about orthogonal modulation schemes like FSK. Okay. So, this is equation for any general modulation scheme. So, how is successive transmission different from one shot detection problem that we have been focusing so far? So, in one shot detection problem, what happened is we are transmitting a symbol, we are receiving the symbol, and then we are bringing down the communication system. In successive transmission, what happens is we are transmitting a sequence of symbols. Okay. And the first question that we have to worry about is whether these symbols are interfering with each other or can they possibly interfere. The answer is no, because we have already solved this problem. So, we have said if these T spaced orthonormal functions are orthonormal to these basic orthonormal functions, then you can safely avoid intersymbol interference. So, this we have seen in lecture 25. So, for avoiding intersymbol interference, this equation must be satisfied. Once you have satisfied this equation, then you cannot worry about intersymbol interference anymore. The second thing is that we are more interested in this detection issue is that if we observe these k symbols at the same time, are we anyway better off than by just looking a symbol at a time. So, for example, if you are transmitting k symbols and if your detector focuses on one symbol at a time, he has got some probability of error, but what happens when he looks at the group of these k symbols at the same time? Is he anyway doing better, or is there some possibility of doing better from just observing one signal or a symbol at a time? Okay. So, we have these bunch of k symbols, and as before we are assuming that this choices that we make is from this signal set. Okay. So, the rule remains same. You want to choose the hypothesis which minimizes the distance from the received vector. So, V is the received vector and uj corresponds to the hypothesis. Okay. This equation is bit complicated, and thus let us try to work this out. So, what we are saying is, let us concentrate on a simple case when we have just two symbols. Okay. So, we are considering a group of two symbols. Let us try to understand this issue, and to simplify this further, let us assume that these symbols that we have can draw values from a binary set. So, either u1 can be minus a or plus a, u2 can be minus a or plus a. Suppose we are receiving two numerical values, v1 corresponding to this symbol that was transmitted and v2 corresponding to this symbol that was transmitted. Now, if we are considering two possibilities of u1 and u2, then we have 4 combinations possible, because u1 and u2 can draw values from binary set. So, we have first possibility when u1 can be minus a, u2 can be minus a. We have a second possibility when u1 can be minus a, u2 can be plus a. We have a third possibility when u1 can be a and u2 can be minus a. We have fourth possibility when u1 can be a and u2 can be plus a. So, we have 4 possibilities and each of this possibility corresponds to a hypothesis. So, we call this as U1, U2, U3 and U4. So, these are 4 possible hypotheses. And what is this minus A? This is the first element corresponding to this hypothesis. Okay. So, just trying to understand the notation. So, if I am considering k symbols at a time and if these symbols are drawing values from a binary set, then the total number of hypotheses that we run into is 2 to the power k. All right. So, when we are transmitting a group of symbols and when we are trying to detect a group of symbols at the same time, then the definition of our hypothesis changes, right. So, each possible group corresponds to a hypothesis, okay. And if you allow these symbols to take any value without any constraint, and if these symbols are taking values from a binary set, if you are considering k symbols at a time, then you have 2 to the power k possible hypotheses. Okay. Now, what we do is we calculate the distance square from each possible hypothesis. For example, let us say we consider first hypothesis. And what is the first hypothesis? In this case, it is minus A and minus A. So, we have to calculate the distance square from this first hypothesis, and this will be V1 plus A whole square plus V2 plus A whole square. What are these V1 and V2s? These are the received numerical values, right. We will be receiving 2 numerical values, each numerical value corresponding to a transmitted symbol. Similarly, we can consider the second hypothesis, and the second hypothesis is minus A and A, and we can calculate distance square from this second hypothesis, which will be this. And similarly, you can calculate the distance square from third hypothesis, you can calculate the distance square from fourth hypothesis. And what is your map rule then? Your map rule is simply trying to find out j for which this t square h of j is minimum. Okay. So, this is your map rule. So, conceptually everything looks simple and similar, there are no differences. Here we are considering the group of symbols as a vector. We are forming a received vector by collecting the numerical values that we have got corresponding to each symbol, and then everything remains same. We are calculating the distance of the received vector from all possible hypotheses. We are trying to identify a hypothesis, or rather choose a hypothesis which has minimum distance or distance square. If distance is minimum, distance square is also minimum. Okay. So, that is what is happening here. Now, you can also express this in another way. For example, I can talk about this norm square of V minus uj. Uj is the vector corresponding to the hypothesis j, and V is the received vector, and this is nothing but it is V1 minus uj1 mod square plus V2 minus uj2 mod square Vk minus uj k mod square. Okay. So, what we are saying? We are saying that the norm square of V minus uj, where V is the received vector and uj is the vector corresponding to hypothesis j, the norm square of V minus uj is simply the sum of mod square of V1 minus uj1 plus mod square of V2 minus uj2 and so on and so forth. What is this V1? V1 is the numerical value corresponding to the first transmitted symbol, and what is this uj1? uj1 is the first element of the hypothesis. Okay. So, we now know that the norm square of V minus uj is simply mod of V1 minus uj1 square plus mod of V2 minus uj2 square, and so on and so forth. So, in short, I can write that norm of V minus uj square is simply sum of mod of Vi minus uj I square, where I will go from 1 to k if we are considering k symbols at a time. All right. So, what happens in one shot detection? In one shot detection, what we are trying to do is we are trying to minimize this. We are looking at one element of a hypothesis at a time. So, we are just concentrating on one symbol at a time, not a group of symbol, and you want to find out the hypothesis, or in this case rather the element of the hypothesis which has the minimum distance. Okay. So, what you are trying to do in short is you are just trying to minimize this one term, and if you continuously use your one shot detector, and if you assume that these elements of this hypothesis are statistically independent, we will see what happens when they are statistically dependent, but let us first concentrate what happens if the elements are statistically independent. So, if we are using one shot detector, we are trying to find out the first element which minimizes this distance, or rather distance square. Then we concentrate on the second element of the hypothesis, we try to identify the second element of the hypothesis which minimizes this distance square. Then subsequently detector will look at each element of the hypothesis, and it would try to do its best to minimize the distance or distance square from the received numerical value, right. So, what would it do is when it minimizes this mod square for each element, it will also result in minimizing this term. Okay. This is the idea, right, that you have to carefully understand. So, what we are saying, this is sum of these terms. One shot detector focuses on one term at a time, tries to minimize that term, and then it looks at the second term, tries to minimize this, and so on and so forth. That means, it chooses one term, minimizes it, chooses second term, minimizes it, and so on and so forth, and it goes up to k terms, look at the kth term, tries to minimize it. There is a theorem, rather a trivial theorem, that if you do your best all the time, you must have done your overall best. Okay. So, if a one shot detector tries to look at a term, tries to minimize it, it will also make sure that it minimizes overall this quantity. Okay. And thus, what we have seen is one shot detector is not anyway different from a detector which is focusing on looking at k symbols at a time. Okay. So, this is rather the conclusion in the case of sequence detection or symbol detection. So, what we are saying is the big goal is to find out hypothesis which minimizes this, and we have seen that this problem is same as trying to minimize this. One shot detector looks at a term, tries to minimize it, it does its best to minimize one term, it continues to do its best to minimize k terms individually. Once it would minimize all k terms individually, it will also make sure that it has overall minimized this term. Okay. So, one shot detection is not any way different from sequence detection if the symbols that are transmitted are statistically independent. So, we can conclude that one shot detection is same as AND symbols detection, but there is one catch. This will not be same if symbols are statistically dependent. If symbols are statistically dependent, then one shot detection will not be same as AND symbols detection. And symbols are statistically dependent in error control codes. So, we have seen some times back that in error control codes, we try to introduce a structural redundancy or dependency so that you can correct errors. That means one symbol is statistically dependent on another symbol, and we try to make use of this statistical dependence to reduce error possibilities. And except in that case, one shot detection is same as AND symbol detection. Okay. So, let us see in case of ECC what happens, and let us take the example of error control codes known as repetition code. So, instead of sending one bit, you are sending 3 bits. So, repeating one bit 3 times. And so, if suppose in this case an error has happened, so a transmitter is transmitting 111, receiver because of some error has decoded this down to 101. Now, receiver gets alarmed because it knows that an error has happened, because it knows that it should find either 3 zeros or 3 ones. It cannot find 101, that is not a possible sequence of symbols in repetition coder. So, repetition coder either transmits 111 or 000, because whatever bit it sees, it repeats this bit 2 times, it transmits 3 same bits at a time, and thus there is some structural dependency. Receiver can look at the sequence in total and it knows that an error has happened. Receiver will not be able to look one bit at a time and tell whether an error has happened, that cannot be the case. So, receiver has to look in totality, it has to look at these 3 bits at the same time, and when it looks at the 3 bits at the same time, it can tell you whether an error has happened or an error hasn't happened. Okay. So, let us now see that we have got 3 received numbers, and these received numbers are minus a plus E1, minus a plus E2, minus a plus E3. E1, E2 and E3 are the error magnitudes, and because of this error magnitudes, receiver is receiving something different from what is transmitted. So, when it is 1, receiver is transmitting minus a, but it is receiving minus a plus E1 because of this error. And once this error magnitude is too large, namely if it is larger than a, then an error will happen. Okay. For example, so whatever we were transmitting is minus a, and if the error magnitude is larger than a, then your received number would lie to the right of this perpendicular bisector, and then you would decide that a possible hypothesis is 0, because the received number lies to the right of this perpendicular bisector, and that will create an error. So, error magnitude or a large error magnitude can create errors. So, there are 2 strategies basically to decode these possible sequence of symbols in case of ECCs in 2 ways. One is what is known as hard decision. So, you look at a bit at a time, so ignore these 2 bits, you take a decision on a bit and you take what is known as a hard decision, that is you cannot change your decision. Okay. So, we are looking at a 1 bit at a time, we are taking a hard decision. We might be deciding for this bit, and in this case we have decided that this is 1. You look down this bit at a time, you take a decision for this bit, you look down this bit at a time, you take a decision for this bit. And then after this you look at what you have got, and now because you know that you should be getting 3 ones or 3 zeros, by looking at this 101 you decide that the possible transmitted sequence of symbols is 111. So, by looking at this you can make 2 guesses, that is what you have to guess. You know that either you can have 3 zeros or 3 ones. By looking at these you better decide for 3 ones, because ones are in majority, right. You better guess that the possible transmitted sequence of symbols is 111. What is the probability of error in this case? So, we have already seen that an error happens when the magnitude of error is larger than A. That will slip down your received symbol to the error plane, to one in which it should not be lying. So, probability of bit error is simply obtained by integrating the PDF of noise. So, noise as usual we assume to have a standard deviation of n naught by 2, mean to be 0, and we are just investigating the situation when this error or noise amplitudes become larger than A. That means you have to integrate this PDF from A to infinity, and let us assume n naught to be 2 and A to be 1 to get some numbers. You can easily see that this will integrate down to, so q of A minus mean is 0, the standard deviation is 1 and A is 1. So, this will boil down to q of 1, and q of 1 is 0.1587. That means about 16% of the time a receiver might make an error. All right, but now you can make use of this structural redundancy, and you can use majority rule, which says that you can always correct an error if only one bit is in error. For example, in this case if you use the majority rule, so here only one bit is in error and you can always correct this to 111, because you decide based on the majority. If you see more ones, you decide that possible transmitted signal set as 111. An error will only happen if 2 bits or 3 bits are in error. If 1 bit is in error, that will not create errors actually. So, let us see what is the probability of error in this hard decision decoding, right. So, when will error happen? When either the 2 bits are in error. So, this corresponds to the possibility of 2 bits in error. So, if 2 bits in error, this possibility is given by p square and 1 bit is correct. So, that is 1 minus p, and you have 3 C2 possible choices, okay, because you want that any 2 bits out of the 3 bits can be in error. So, this term corresponds to the probability of error when the 2 bits are in error, and to this we need to add the possibility of 3 bits to be in error, and this possibility or probability is simply given by p cube, where p is PBE. Okay. Working this out, what we have got is probability of error in hard decision decoding is 0.067. So, what it is doing is it is looking at this group of 3 bits, it is trying to use the structural redundancy that is inbuilt, and using that structural redundancy it is trying to correct the code or the received symbols. Okay. And so, it will be able to correct until and unless, in this case for example, 2 or 3 bits are in error, and this probability is 0.067. So, it has reduced the probability of error, which was around 0.16 to 0.067. So, that is some saving. Now, let us see what happens. So, this was in hard decision decoding. Let us see what happens when you are looking at the group of 3 symbols at a time. So, now we are not doing hard decision decoding, we are doing something which we call as soft decision decoding. Soft decision decoding is more optimum than the hard decision decoding, okay, and this we will see. So, when we look at 3 symbols at a time, probability of error occurs when the distance of the received vector from the hypothesis 1. So, this corresponds to situation when hypothesis 1 is transmitted. Okay. Let us look at this. So, when hypothesis 1 is transmitted, you are transmitting 3 ones, and when you have 3 ones, you have 3 minus a, and let us say the numerical values that we have is v 1, v 2, v 3. So, what is the distance square from this hypothesis 1? The distance square from this hypothesis 1 is v 1 plus a square plus v 2 plus a square plus v 3 plus a square. Okay. We are assuming everything to be real, so there is no need of mod and so on and so forth. So, this distance square corresponds to the case when hypothesis 1 is transmitted. So, this situation corresponds to the case when hypothesis 1 is transmitted, and this is the distance square when hypothesis 1 is transmitted. Similarly, this is the case when hypothesis 0 is transmitted, and this corresponds to the distance square when hypothesis 0 is transmitted. And probability of error will occur when this distance square is larger than this distance square. So, why is this? Because we have transmitted this hypothesis 1. So, given that we have transmitted this hypothesis 1, this distance square should have been smaller than this distance square, because my detector would anyway choose the hypothesis for which it has got the minimum distance or distance square. If this distance square is larger than this distance square, then detector would choose hypothesis 0, and this will create an error situation because we have transmitted hypothesis 1. Okay, that is the premises. We have transmitted hypothesis 1, then what is the probability of error to take place? Okay, and that would happen when detector choose hypothesis 0, and it would choose hypothesis 0 when this distance square is smaller than this distance square. All right. So, let us expand this and see to what this condition translates to. So, just expanding terms, assuming everything to be real. So, I will not read it out, you can stop the video and work out this arithmetic yourself. So, this simply translates to the condition that E 1 plus E 2 plus E 3 should be greater than 3 a for error to happen. And what is this E 1, E 2 and E 3? These are the error magnitudes corresponding to the symbol 1, symbol 2 and symbol 3. So, notation remains same. So, what I am saying is that if we start from this basic equation, cancel some terms, reduce this equation, you can simply find that this condition simply translates to the condition when sum of these errors, that means E 1 plus E 2 plus E 3 should be larger than 3 a for error to happen. And to simplify stuff, let us define error as E, which is sum of E 1 plus E 2 plus E 3. If you are summing the bunch of independent Gaussian random variables, each error corresponds to a Gaussian random variable. These errors are also independent. Error happening in one symbol is completely independent of error that will take place in second symbol. So, these corresponds to independent Gaussian random variable. So, E is also a Gaussian random variable. What is the variance of E? So, variance of E is just 3 times variance of each error, right. So, if we assume that E 1, E 2 and E 3 has a variance of n naught by 2, this is what we always assume, then the variance of E is simply 3 times n naught by 2, right. Variances add if the underlying random variables are independent. And if we assume n naught as 2, then the variance of E is simply 3. What is the mean of E? At 0, and hence we can model E as a Gaussian random variable with variance of 3 and mean as 0, is not it? Now, to estimate the probability of error, you need to find out what is the probability of error when the error magnitudes becomes larger than 3. So, it goes from 3 to infinity. However, you have to substitute the new variance is 3. So, I have to have 3 in here, 3 in here, and what is this integration? So, this is q of 3 minus mean is 0 divided by standard deviation, which is root of 3. So, this is simply q of root of 3, which is 0.0416. Let me look at what was the result in hard decision decoding. So, let me write down this here. So, this was in hard decision, and this is in soft decisions, and you have got that when you are considering 3 bits altogether, you have been able to reduce errors. When you consider 1 bit at a time and then you use the structural redundancy of the code to reduce errors, you could reduce it to a number like 0.067. It is also small error probabilities. If you consider that you have dropped this down from 0.15 to 0.067, that is lot of good, to even a smaller number 0.0416. Hence, we sort of have got this idea that looking at the 3 bits at the same time is much better when the bits and the symbols are statistically dependent, and this is the idea. We will talk more about soft decision decoding and hard decision decoding later in the course. At this time, I am just trying to establish the fact that if you are transmitting n symbols and you want to look down these n symbols at the same time, it is only useful when these symbols are statistically dependent. If these symbols are statistically independent, whether you minimize the distance for each symbol or you minimize the distance for n symbols at the same time, it is one and the same thing. If you do your best each time, you would be able to do your best collectively. Okay. But when these symbols are statistically independent, we can use this statistical dependence to look down this collection of symbols at the same time, and we can reduce the probability of errors. So, with this we have come to the conclusion of this lecture, and in this lecture we have looked into the rules for detection of waveforms, and then finally we have looked into detecting n successive symbols. We have seen that detecting n successive symbols is no different from detecting a symbol at a time when the symbols are statistically independent. However, when the symbols are statistically dependent, it is a good idea to look at these symbols collectively, and we have seen a strategy which reduces the probability of errors when the symbols are looked at the same time holistically. So, in the next lecture we will start by looking into the performance of ML signaling schemes, and we will start with binary signaling schemes. Thank you.